Okay, let me start. And I like to start reminding you guys that when you look up in the sky and you see stars, you don't realize that every single star out there is not naked, but it's surrounded by a cloth. What is that cloth? That cloth or that cocoon is formed by the wind that emanates from every star. Stars are not static, they move. So the wind that they emanate get deflected, forming a cocoon. And we call that cocoon astrosphere. It's hard to detect them, but here are some images from NASA of detected astrospheres. We also have one. So the sun has a wind. We're also moving through the interstellar medium. So we have a cocoon, and we call it the heliosphere. So I'm going to tell you all what we're learning about the heliosphere. But before I do that, I want to remind you that we are looking for lives in other planets. This is one of the frontier in astronomy, another Earth-like planet. So far, we haven't known one, we haven't met one, so we are the only habitable astrosphere. So we better understand that astrosphere. If we want to understand how other life evolve in other planets, we better understand the influence of our own cocoon. We know that cocoons are important, those astrospheres. And I will tell you in a minute why. And here is a movie that shows you how the heliosphere look like today. I will tell you at the end that we don't think the heliosphere was like that in the past. But right now, this is what we think the heliosphere look like. It's engulfed all the planets in the solar system. If you want to have an idea about the size, it's around 150 times the distance between us and the sun. So it's big. And here the movie is going to run again. One of the goals of SHIELD, this is one of the NASA Drive centers, is to try to understand everything we can about the heliosphere and relate to it how life formed on planet Earth. So you can check our website here. Okay, why do we know that astrospheres are important? They know they protect planets. Here is a mosaic showing on the nearby stars, our neighbors, the indirect detection of astrospheres. And when the Voyager spacecraft, Voyager 1 and 2, were launched in 1977, they're still taking data, and here is the data of the radiation that come from the galaxy. Just to give you an idea why it's important, this radiation, we call it galactic cosmic rays, is the #1 radiation that is important for astronauts for long-term voyage. So when we send astronauts to Mars, to Moon, if they spend more than 3 years, this is the #1 radiation. This is why NASA should care about it. So that radiation, Voyager measured up and down, going in the solar system, and in 2012, Voyager 1 left the heliosphere and the radiation jumped by 70%. It means that the heliosphere shields 70%. We cannot right now predict this radiation, how the heliosphere shields. We are trying to understand that. The properties of the heliosphere that makes this shielding. Not only the heliosphere shield radiation, it's also shield dust. I'm not going to show it here, but you can see how the dust go totally filtered. The small dust is filtered by the heliosphere. So how did we learn about the heliosphere? We learned with many, many missions that NASA led. One of them, the Pioneers, going back to 1995, 2003. The Voyager spacecraft that I mentioned that were launched in 1977 still are taking data, and they left the heliosphere in the nose direction. We also have energetic neutral atoms that we can measure the heliosphere. It's around Earth, but we take line of sight, and like in a tomographic fashion, we can see the heliosphere. This is the IBEX mission, Cassini mission, and we are very excited in 2025 with the IMAP mission coming on board. And we also have New Horizons that is still not at the edge. It's taking data with some instrumentation that Voyager didn't have, so we're very excited with that. And we hope we will have a new Voyager, an interstellar probe that will come revisit that region with a modern instrumentation. So what did we learn? There's a lot of puzzles. We learned that how little we know. So we created this center called SHIELD with the big lofty idea that at the end we will be able to create a digital twin of the heliosphere. How do we do that? We do that by collecting observers from all these missions I mentioned, theoreticians, modelers, and the problem is that the heliosphere is huge. So we need modelers that model the big structure, but all what's going on, it's also mediated by small physical processes that happen in a very small scales. So we have experts in big modeling and also small processes like reconnection, turbulence, and all these observers trying to understand questions like how far we have to go from the heliosphere when we leave the heliosphere, go to the galaxy until we forget about the heliosphere, until we are in a very calm galactic medium. We don't know. And this is in a bigger picture, how far you have to go away from an astrosphere of a star to forget about that astrosphere. We don't know. So this has implications for astronomy, and major ones. Okay, I'm not going to talk about all the amazing science. I'm going to mention one problem we have that I think will bring home how we are making the first steps, baby steps, to wrap around our knowledge of the heliosphere. And this has to do even with the shape of our home. And it's a little embarrassing. You ask yourself, do you know the size of your home? You said, yeah, I know, it's 1,600 square foot. Here we don't know. We know the nose. We know because Voyagers left, so we measured this little piece here and here. The rest is on theory and modeling. We don't know. So if you Google heliosphere, you get the canonical picture from NASA saying we have a very long tail that extends forever on the opposite direction of the nose. Turns out that in the last couple of years, with the energetic neutral atoms, the tomographic image that I told you, plus the modeling, we have started thinking that perhaps, see if I can advance it. I cannot. Can you advance it? Oh, it's advancing, great. So we started thinking that maybe the shape is much smaller. So here's the nose, this is kind of flipped. So this is a nose, and the tail is much shorter. And perhaps it's a crescent. I like to call it cosine, heliosphere, but it's probably a very different shape than we thought. Why do we care? Why NASA should care about the shape? Because this probably is mediating how much radiation comes into the heliosphere. So if we want to be able to predict for an astronaut sitting on Mars how much radiation is going to feel, we better understand that. Okay, I talked to you about all the puzzles of today, but now let's take a step back. The sun is not an immobile structure. It's moving around. And its speed, now units you might not be familiar, but this 18 parsecs per million year is the same speed that the Voyager spacecraft is leaving the solar system. It's pretty fast, okay? And it's mean the sun, if you go 1 million years, this is only the neighborhood of the sun right now. 1 million years ago, the sun is out of this neighborhood. Think about yourself. You're not living where you grew up. You're not going to stay here forever. You might move around, and you shape, you evolve, you're a different person as you move. The sun is like that. So we started asking the question, what happened to the sun in the past, and what will happen to the sun in the future, and its heliosphere as we move around. One of the interesting things to realize, this is our closest neighbors in your street. But think about in your country, where do we live? The sun right now is embedded in a huge shell called local bubble. Let me see if the movie can play. The sun, right here, the yellow, is sitting here a gigantic shell that is a result of 14 million years ago explosion of very massive stars. So look at the clock there. 14 million years ago, a bunch of stars died, exploded, and all this shell started blown away in space. And as a bomb that goes off, it started sweeping material where stars are forming at the edges. Well, our dear sun was walking around and around 6 million years ago encountered that shell. And the obvious question is to ask, what happened to our heliosphere when we go through a blast like that? So here are the regions of where stars are formed, showing you that the edges of the shell are very dense. So we set to model it, and what I will show you is a result of such encounter. The heliosphere shrink. Here is a heliosphere 3 million years ago and 7 million years ago, where we think the heliosphere completely collapsed. Here is Earth. We are unprotected. We are outside in the interstellar medium. This is a trajectory of Earth, and you can see here sidewise. The heliosphere is a green little bubble here. It's less than 1 EU. This is a distance of us to the sun. We were totally exposed to the interstellar medium. So think about it. We are exposed, massive hydrogen atoms coming to us, massive radiation. And the question we are trying within SHIELD is to relate that. What will happen to the climate? What happened to the human evolution at the time? So you can ask yourself, how do I know what happened in the past? Well, I know about the temperature on Earth from these little creatures. Those are called foraminiferas, so little shells that you can scoop from the deep ocean, and depending on the number of chambers here, you know the age of the shell, you can measure isotope, and you can relate that to the temperature of Earth going back 15 million years ago. So I think this is the next frontier, is to relate where the sun was, and the sun indeed moves a lot, to what's happening on Earth. And that time, just to remind you, this is where a lot of things were happening in human evolution. 7 million years ago is where these people, the Lucy, went extinct. And one of the connections that people do when they're studying that the climate changed dramatically. Would be interesting if the climate change has an effect of what the heliosphere was doing. So more to be seen in the future. I hope you get engaged with us, studying the heliosphere of today and in the past. Here is all the social media. We have lots of activities. I didn't talk about the outreach piece here. So I'm just leaving this slide here. One of the other major thrusts of SHIELD is to try to answer those questions with a diverse community. Is bring to the table different voices from different origins, just science thinking, but also upbringing different. And I hope you can see by the mosaic of faces, we are starting to do that within SHIELD, and we hope to inspire the broader community of space physics that this is critical. I think I'm going to end here and open for questions.